Let's review on the Bode diagram, Bode plot. Or Bode diagram. So, what is this Bode diagram for? It represents frequency. Characteristic of a dynamic system. And it's a plot, semi-log plot of dB versus frequency and phase versus frequency. Okay, and what is dB? dB is defined as 20 log 10 of the magnitude of the frequency response functions. So, why do we use? In other words, Bode plot, you should have two of them. Magnitude part, you have dB versus frequency, dB. Okay, and this is log, in log. And also, you have phase angle versus frequency. This is in log scale. So typical questions to ask is, why do we use log? Log in x-axis. Well, it's like, why do we use log in the fatigue strength? Remember, we have endurance limit. This is end cycle. But this is endurance limit, fatigue strength. And this is in log 10, 1000 to that's million. So why do we do that? Well, we can cover a wider range of data. That's in x-axis. How about then, why do we use dB? dB in y-axis. Of course, we remember the dB is defined 20 log base of 10 of transfer function. So why do we use that? Well, because the log function, you can convert multiplication into summation. So why is that? Remember we talked about in 340 or 3401, we only talk about first order and second order system. We didn't talk about higher order system. Why? Because as long as we can know first and second, the high order system can be a combination of the first and second order system. So when we use this log, let's say log A times B, then you can convert A, B. So multiplication into summation. So if I have a higher order system, when you do log 20 log, let's just simply make an example as third order system, tau s plus 1. So you can easily break this into three subsystems: a constant with another first order system, another so higher order system, it is as a third order system. You break it into one first order, another second order combined. So as long as we know the basic or the first or second order system characteristic for higher order system, we can always add them together to find the overall. Okay, so that's why we use a Bode plot, and of course, using Bode plot, we can do a simple, easy hand drafting, and you can identify the system, through the slope. Okay, so a lot of time situation is we don't know the systems. And we can run a signal input, sinusoidal in, sinusoidal out. Okay, and from the Bode plot or output over input, and you come back to determine the system models. Let's say you run 5 Hertz, output over input in magnitude, output over input at different frequency. If this is second order system, you should probably get this curve. And of course, you can get a phase. So based on Bode plot, we can test the system to identify the test. Run the test since input and get an output over input, you can get a system model or identify the system. let's talk about the basic subsystems. The most common is first one, if it is a constant k. So in that case, dB wise will be 20 log k. Phase is 0. So you should get so this is in omega in frequency, this is in dB, so you should have this point would be 20 log k in dB. Phase angle wise, it's always 0. This is 0 phase angle wise. So how about if you have these 1 over s, which is integrators. So the magnitude Ti omega, that will be 1 I omega. So let's put it in magnitude and phase 1, phase angle 0, omega, phase angle 90. So you should have 1 over omega, angle wise minus 90. So if we put this it's always minus 90. That's 0. It's phase angle dB. So omega equal, so dB should be 20 log. So omega equal to 1, that's 0. So it's always this equal to 1, that's 0 dB. Omega equal to 10, 1/10. So this one should be minus 20. If you put another point, omega 0.1, that's positive 20. In other words, you should have a line passing through omega equal to 1, omega equal to 1, a negative slope. And you know the slope, we can say every 10 times from 1 to 10, 1 to 10, the drop is 20 dB, so it's minus 20 dB per decade, minus 20 dB, okay? So, meaning 10 dB dropped every 10 times of frequency. From 0.1 to 1, 10 times. The drop is 20 to 0, right? 20 dB. Okay. So, how about we have another one? So with this, of course, you also can find out if you have differentiators. S called differentiator. So simply Ti omega is I omega. S by M. Put it in magnitude and phase. Omega, phase angle, positive 90 degree. So opposite to integrated. Omega equal to 1 to 10 should be positive 20 dB. One 10.1 omega dB, phase angle phi should be always 90. So this one here is minus 20, 0, positive 20. So the slope here will be positive 20 dB per decade. 20 dB increment, positive increment per 10 times of frequency. Okay. So let's look at the first typical first order system. Tau s equal to 1 over tau s plus 1. Okay. We use the standard subsystems. Okay, got to be in this form. So Ti omega should be 1 tau I omega plus 1. Let's do it quickly. 1, 0, magnitude 0, and amplitude real square plus omega tau square, phase angle, arctangent, real over imaginary omega tau. So we get the one we have earlier, 1 plus omega square tau square arctangent minus omega tau. So that's this. So 20 dB. dB would be 20 log 10 1 plus omega square tau square. Phase is minus tangents omega tau. So let's use this. So let's do 3 regions when omega tau much smaller than 1. In other words, low frequency range. What happened? This term goes away, so you should dB should be 0. What happened to omega tau equal to 1? Phase angle. Phase angle should be close to 0, so this is 0. How about this? Equal to 1. So 20 log 1 over square root of 1 plus 1, 2. So this is what we have the famous point, 3 dB minus 3 dB. How about phase? Phase should be 0. 1, arctangent 1, 45, so should be minus 45 degree. What happened? Omega tau much greater than 1. In that case, these terms, 1 goes away, your dB become 20 log 10, 1 over omega tau. In this case, what if in this range, what if I increase omega 10 times by 10 omega, from omega to 10 omega? So the new dB will be 20 log 10, 1 over 10 omega tau. So again, convert this into summation will be 1 over omega tau plus 20 log 1 over 10. So when I increase omega 10 times, I get the original values, omega tau, and drop this value, which is 20 dB. 20 dB. Okay, this range. How about phase angle? Much greater than 1. That's greater than 1. So this becomes infinity, much greater when omega goes to infinity. So in that case, you should have minus 90 degree. So with these three, we can do the quick analysis. Quick drawing for the Bode plot. So first of all, dB plot and phase angle. So starting from cutoff frequency, how do we get cutoff frequency? That's right here. So omega tau equal to 1, meaning omega equal to 1 over tau, we call cutoff frequency. Tau frequency. Okay, so this is the key point for the first order system. So from 1 over tau cutoff frequency, before 1 over tau is 0 dB. After 1 over tau, 10 times more, 10 over tau, you have 20 dB. So this is 0, this is dB, this is omega. So that's why we said the slope right here, flat and drop, negative, so minus 20 dB per decade after the cutoff frequency. Same thing for phase. At cutoff frequency, it's always minus 45 degree, and 10 times more, It's 90 minus 90, 10 times less would be 0.1 over tau would be 0 dB. So for some reason I have the light coming. Okay. So Bode plot before, that's 0, after, that's minus 90, and this is the straight line. 0 minus 45, positive minus 95. Or sometimes we said minus 45 degree per decade. Okay, so we know the system parameters, and then we can quickly find the Bode plot. For example, let's say I'll just draw a quick one. If I want to know what's the Bode plot of 1 over 0.1 s plus 1, we don't need to do all the analysis right here. All we need to do is identify what's tau, and then we can find it. So tau equal to 0.1. In that case, cutoff frequency omega c would be 1 over tau would be 10 radian per second. So simply we draw the Bode plot. You can go from 10 to 100. The drop is 20 dB or minus 20. Phase angle from 10 to 100 is minus 45, 190, 0, that's 0, oh, sorry, 1. So quickly I can draw flat slope, and minus 90 for the Bode plot of this particular system. So we don't need go through all these calculations. Just simply identify tau, know the slope, and you can find the Bode plot easily. Okay, and one thing to specify is this is approximation. This is what we call asymptote. Asymptote. Okay. For exact case, exact situations, for first order system, we should have this one and then a curve, and we should have this one as a curve, and for the exact point at cutoff frequency, that's the so-called minus 3 dB. That's why we always say this is a famous point. But asymptote is a 1 for approximation.